Alright, so we have the two-way table. We already done this. Two number cubes are rolled one at a time. Here's their sums. Alright, suppose event A is rolling a 5 on the first row, and B is rolling a 4 or less on the second roll. Okay, does everybody understand our situation? Determine the probability of rolling a 5 on the first roll and rolling a 4 or less on the second roll. What is the probability of rolling a 5 on the first roll? So, and then it says, shade the desired outcomes and draw a border around the possible outcomes. Explain your reasoning. So what is the probability of rolling a 5 on the first roll? And if I was coming over here, what would it be? It would be the first roll, correct? So is it this 5 that I'm concerned with? Why? What does this say right here? Second roll. It's what? This 5 right here. And where are all the outcomes at? So if I was going to shade them in, like it asked me to, it doesn't do a good job. If I was going to do something with that, I would do this. Be this whole thing that I'd be shading in. Correct? Let's go. You have a book. You should be shading it. Right? So if you see right here, this is where it's hard to see the shade in, but it is shaded in. You can see it shaded in right here like we did. And then what is our outcome? It would be 1, 2, 3, 4, 5, 6 out of the 36, which reduces down to 1/6. By the way, in order to figure out the probability of a 5 being rolled the first time, how many events are there that are desirable? How many 5s are there? 1 out of how many different things are there on a dice? So doesn't it make sense that it's 1/6? Do they have to do all of these right here? Or could you just think of it that way? You could just think of it the way I just showed you. Alright? Look at the next part. What is the probability of rolling a 4 or less on the second roll? Shade the desired outcomes. Okay, so if I was going to do a 4 or less, what numbers would work, Tom? I'm doing 4 or less. What numbers would make that true? What numbers would it be, Tom? Okay, so it would be, if you go up here, you see them shade all of this section right here. So for this event, how many different outcomes are there that I want? Since I'm only worried about the second number cube, how many numbers are 4 or less? How many numbers are 4 or less? Well, what'd you say? 4 of them. 1, 2, 3, 4. Out of the how many numbers are on the number cube? And what does 4/6 really reduce to? 2/3. If you count all the boxes, you'll see that there's 24 out of 36, which also reduces down to a 2/3. Does that make sense? This should not, by the way, this should not take us long. I'm not teaching anything new. There's nothing new up here. What is the probability of rolling 5 and a 4 or less? Well, do you see how they shaded this spot in? Let's do it. So we'll do this spot right here. All these boxes will work that are inside this one. Right? All these will work. Correct? Whereas that's for the second one. The first one is this right here. Where's the overlap? Where's the overlap? These 4 boxes. Right?
Yeah.
So, how many of them make both of them work? How many of them meet that criteria? 4. 1, 2, 3, 4 of them meet that criteria out of? How many total outcomes are there for this one now, Will? This is the and. There are 36. 4 out of 36, which reduces to 1/9. Alright, so just again to review this is the way we're doing it with the boxes, but the real math that we've talked about is, we said the probability of the first one happening was 1/6, and when we have an and, you take those two and you multiply it. So the probability of rolling a 5, which is event A, or rolling a 4 or less is probability B, which we said was 2/3. This is middle school mathematics. How do you multiply them? You can cross simplify. This becomes a 1. This becomes a 3. 1 times 1 is 1 over 3 times 3, which is 9, which is the same thing that we got when we counted them. But we're not going to be able to count all the boxes. We should know this. And all of this is review. None of this is new. We've already done all this. There they show calculating it by actually doing the real math. All right. A conditional probability is the probability of event B given that A has already happened. So, the probability of rolling a 4 or less on the second roll, given that 5 is rolled first, is an example of conditional probability. The notation for conditional probability is this. Right here. Which reads, the probability of B given A. Does everybody see that? Now, this really won't affect too much when it comes to independent events, which is I think what we're going to talk about. Like, right here. I think that's what they're going to get into. If I know that a 5 is rolled first, does that change the possible outcome of the second one? Does me rolling a 5 the first time change my outcome of me rolling a 4 or less for the second? So what's still going to be my probability of rolling a 4 or less given that I have a 5? What was it before? Not the 1/9. 1/9 was both of them happening together. What was the probability, look back in your book, of rolling a 4 or less? Well, there's 4 possibilities out of a total of 6. What does 4/6 reduce down to? 2/3. Right? So what do you notice about these guys? The probability is what? The first time, when the probability of rolling a 4 or less, the second roll, it's the same as if it's, do you get what I'm showing you? It's the same, it didn't change. Why? Because event A really had nothing to do with event B happening. Doesn't make it better, doesn't make it worse, it doesn't change it. Does that make sense? Now let's talk about our marble situation. You know, we pull marbles out, but we don't replace the marble back in. Would that change my outcome? Yes. Do you get what I'm talking about here? That's what they're saying. That or means equal. Alright. So, what do you think? They're independent events because the probability of A or B given A is the same as probability of just B. That means the occurrence of A does not affect the probability of B, so the two events are independent. A has no bearings on B. Rolling a 5 does not change any of the facts of me rolling a 4 or less for the next roll. Does that make sense? All right, suppose A is rolling a 5 on the first, and B is rolling a sum greater than or equal to 8. So what is the probability of rolling a 5 on the first roll? Shade the desired outcomes. Should be 1/6 still. Does that make sense? Okay. What is the probability? Now this one, what is the probability of rolling a sum greater than or equal to 8? Shade those. Well, that's why we're going to shade all the ones that have a 8 or higher in the boxes, because that's their sums. Does everybody understand why those are? And there's 1, 2, 3, 4, 5. So it looks like 1 plus 2 plus 3 plus 4 plus 5. Yes? And so when you add that together, you get 15 out of 36. 15 and 36. Please don't just focus on the coloring. 15 out of 36 reduces because 5 goes into both, or 3 goes into both of them. This reduces to a 5 and a 12. All right, what is the probability of rolling a 5 first and a sum greater than or equal to 8? And so we shade those desired outcomes. And if you notice, it's right here where you roll a 5. Remember this? So why is this box colored in? Why is this one, why are the 6 and the 7, why are those colored in? Because my first thing is a rolling a 5 first. So that would be this one, right? Does everybody understand what I'm showing you? Then the next one is a sum of 8 or greater, so we go to this, like this, we go this section right here. Where is the overlap? The overlap is where the black and the red, those parts together, so it's only these 4 boxes that meet that criteria. Are you with me? So it's 4 out of 36, which reduces down to 1/9. You with me? Now, what is the probability of rolling a sum greater than or equal to 5 or 8, given that a 5 was rolled first? Now, how many events are there now if I know a 5 is rolled first? So this was out of 36, correct? This is out of 36. Now my possibilities. I've told you that how many different events, I've told you one of the things has already happened. Does that make sense? How many events do I have to have filled in then? That's how many total there are. How many events do I have? So I roll a cube and I roll a cube. There's 2 events, correct? I already told you the first one. So how many events are left to be filled in? 1 of them. What's the only thing we have left to do? Roll the second number cube. Does that make sense? How many different outcomes are there for rolling the second cube? There's 6 of them, correct? So if I go down here, I'm going to go to your book for just a second. Hold on. All right, so I'm not using the right page, but this is still the same thing. I've already told you this has happened. You already know when you roll first, you have rolled a 5. That's not a question. That's exactly what has happened in this case. So how many different outcomes are there for this next event? 1, 2, 3, 4, 5, 6. Does that make sense? Because with the second one, I can roll 1, a 2, a 3, a 4, a 5, or a 6, correct? What is my second outcome that they want? An 8 or what? So if I go in here and I go, okay, this is an 8 or higher, I would color all these boxes in. What are my chances of that happening? 4 out of 6. The reason it's not out of 36 anymore is because you don't have a chance of rolling a 1 on the first roll. You don't have a chance of rolling a 2, a 3, a 4, a 5, a 6. What is the only case that you have for the first roll? A 5. You know that's what happened. So that event is already filled in. So what is the only event that is affecting our outcome? The second one necessarily? Does that make sense? So there's only 1, 2, 3, 4 that are desired out of the 6 that could possibly happen. And what is 4 out of 6 reduced to? 2/3. Now, what's the next question they are going to ask you? Please, someone remember what we did prior and what they're going to ask now. They're going to say, are these two events independent of each other? Well, last time, when I did the probability of B happening, it was the same thing as the probability of B when I was given A. They were both the same probability. What was the probability of B happening? What was the probability of B happening just by itself up here? Probability of B was right here. This right here is probability of B. Do you see where it says it right there? And the probability of B is rolling an 8, or the sum of them being 8 or higher, correct? And there was how many of them? 5 out of 12. Now I go down here, because I know they're setting me up for this question, and they say the probability of B given A is now what? 2/3. Is the probability of B the same thing as probability of B given A? No. So are these events independent of each other? No, they're not. Why? Once I told you that A happened, what happened to your chances of rolling an 8 or higher? So let's go up here. I just say, what's the probability of the two things being 8 or higher? Your chances are 5 out of 12. If you do this 12 times, you're going to get 5 of them that work. The other 7, you're going to fail. Does that make sense? Are those good chances or not very good chances? They're less than 50%, because 6 out of 12 would be half. You with me? Yes? And now I go down to here. What happened when I gave you the probability of, or I gave you, you're going to roll a 5. What are the chances that you're going to, that some of them is going to be 8 or higher? 2/3. That means you could do this 3 times, and how many times are you going to get it correct? Is that higher than 50% or lower? It's quite a bit higher. It's around 67%. Whereas the other one was probably around like 42%, somewhere in there, 43%. Are you with me? Are those two probabilities the same? No. Then the first roll has some kind of the next thing happening. Rolling the sum of them being an 8 or higher has the first roll has some kind of effect on the being 8 or higher. They're dependent on each other. Okay? Like, let's say this. Let's go here. What if I told you, you roll a 1. I'm giving you the first roll, you roll a 1. What are your chances of you rolling an 8 or higher? The sum of them being 8 or higher. There's no chance. When you roll a 1, what's the highest you can get to? So do you have any shot of getting an 8 or higher? No. Why? Because your first event has effect on the second event. Now, my second event is, I'm not trying to get a number, am I? I'm trying to add the two numbers together. So you get what I'm talking about here.
So like
So right here, when we compare the two probabilities, it's a 2/3, it's a 5/12. Those don't equal each other. What does that mean? That means the two events are dependent on each other. Does that make sense? So if I said, what are your chances of rolling, when you roll two dice, of the sum of them getting 8 or higher, and you roll a 1, and we're playing a game, why are you mad? You're like, dang it, I lost. I'm out. I got no shot. Right? What if I said, hey, we're gonna play a game. Okay? And you can, on your second roll, if you get a 3, you're still in the game. So you roll the first number cube, and you don't get one of the desired outcomes. Okay? There's an event A and there's event B. So you roll the first one, and it doesn't work out for you. Are you out of the game? You can still roll a 3, and you're still got a chance. So A had B event didn't depend on A event. You still had does that kind of make sense? Like that might help you understand the dependent or not dependent? All right. When two events are independent, the probability of B given A is equal to the probability of B. When two events are dependent, the probability of B given A is not equal to the probability of B. And that doesn't mean the probability of B given A is always higher. That doesn't mean that. That just happened in our case. It just says they're not what? Hello, what does this symbol mean? They're not equal. Can this one be higher than this one? Yes. Can this one be lower than this one? Yes. They just cannot be what? Equal. So your given A doesn't always increase your chances. Sometimes it's going to what? So sometimes it's going to lower them. You with me? All right. Now you can derive the formula for conditional property. So let A represent the event of rolling a 5 on the first roll and B a less than 4. So we're going back to that problem. A 5 on the first roll and a 4 or less on the second roll. Complete the probability table right here. So the desired outcomes, there's 6 of them. There's 36 total outcomes for this. Why did it all of a sudden become probability of B given A? Why did it go down to 6? Why does this one go down to 6? Because what? Because now I know that I've rolled a 5. There's only 6 other things that can happen when I go to roll my second dice. Yes? This one there's still 36. This one there's still 36. Because how many events am I filling in this right here? See, I wish they did that a little different. See, if it was me, can I be honest with you right here? I don't like this. If this was me, how many total outcomes for probability of A? Probability A is rolling a 5. Does that make sense? How many different outcomes are there for me? I would say that there's 6. Because how many dice am I rolling? 1. So how many outcomes are there? 6. How many desired? How many 5s are there on that dice? And so that's how I would get my 1/6. Does that make sense? Right here, this one, this is 24. This one right here says, no, it's not. I lied. We're good. It says probability of rolling a number less than 4. How many dice am I rolling to get probability of B? 1. How many less than 4s are there? 4. How many outcomes are there? 6. 4 out of 6 reduces to 2/3. I think that's how this should be filled out personally. Now, yeah, I think it should. Now, probability of A and B, how many events am I filling in this one? You're filling in 2 events. You have to do A and you have to do B, right? What's the probability of A happening? 1/6, right? How many probability of B happening? 2/3. This is what we already did, and that reduces down to 1/9, yes? And how many events are there that I'm filling in? We said 2, right? How many different outcomes are there for rolling the first number cube? 6. How many for the second? 6, which gives us that 36. This one is out of 36, so I'm rolling 2 number cubes. Where in this one, I'm only rolling. So I disagree with the book on this. Does that make sense? I think they do it because of the chart that's up here. But I don't know. I don't see why they do make you do that. All right. So use the table to verify. They can still get the 2/3. We've already done this. All right. This is the thing that we need to. They show you how they derive to this, but this is what we need to be concerned with. Conditional probability for independent events can be written as this. Right here. Probability of A and B divided by the probability of A. But what is this for? Does that make sense? Alright, Michael says the probability of rolling a number less than or equal to 4 on the second roll given A is equal to the probability of rolling a 4 or less 4 or less than equal to 4 on the second roll, probability B. So he's saying that probability of B given A and probability of B, those two things are equivalent. They're equal. And he says the reason is because they are independent. Is he correct? Yes. Conditional property is equal to the probability of event B because the outcomes of A do not affect the outcomes of B. So, the formula that they just came up with, which is, I'm curious on how we're going to, yes. So right here, what happens when you have probability of A over probability of A, and there's a multiplication between these guys? Please understand this is huge. Probability of A plus the probability of B divided by the probability of A. Do these things look the same? Do these things look very similar? Yes. Can I cross this probability A and this probability of A out? No, because of this addition sign. There would be parentheses around this, and I would have to do this addition first, then I would do this division, which is right here. Does that make sense? I know this is really division. But right here, this is really multiplication and division. You with me? And so I can cancel these out. And that's how they get the probability of B just left over. Alright. Can we depend on conditional probability? Let's see what the formula works for actions affected the desired outcomes. Alright, so suppose you have 2 red socks, 1 blue and 1 yellow. You randomly choose a sock without replacing it. Then you randomly choose a second sock. Okay. How many events are going to happen? 2, right? You're picking 2 socks. How many outcomes do you have for the first one? 2, 3, 4, right? How many do you have for the second one? 3, which means there should be a total of 12 different events that can happen here, right? And that's what they do. And they give you an organized list to show you all the different ways. Yes? Yeah. I'm going to go quick through this. All right, what's the probability of randomly choosing a red sock first? Well, how many different red socks are there? There's 2 out of 4. 2 out of 4 reduces to a 1/2. Does that make sense? What is the probability of randomly choosing a red sock second, given that a red sock was randomly chosen first? Okay? How many events are being filled in this question? 1. How many socks are left in the drawer? How many socks are left in the drawer? 3, because I know that 1 is what? What's gone right now?
1 red sock.
1 red sock. Does that make sense? Okay? How many red socks are still left in there? So, do you understand how we got a 1/3? Now, what is the probability of choosing a red sock first and a red sock second? Well, there's a there's a 2 out of 4 chance for the first time, right? Times, because we do it, 1 out of 3 chance for the second one, and that becomes 2/12. And what does 2/12 reduce to? 1/6. Does everybody understand where we're getting this from?
Yes.
I'll finish this while you guys are gone in between classes. Finish the video. It's at 31 minutes.
All right, have a good day.
See. Are events A and B independent or dependent of each other? And so we know that A and B are dependent because when I go back here, the first sock has effect over the picking the second one, because if I go back to the probability of just B, the probability of just B happening was so events A and B are dependent because the result of picking the first sock has an effect on the outcome of picking the second sock. So the two probabilities are not going to be equivalent. It's the probability of randomly choosing a second sock given that a red sock is randomly chosen first. Are those two equal using this formula? So what they do is they go down here, and we know the probability right here. We know the probability of where's that? Right here, probability of B given A is 1/3, so we know that fact. So down here, we already know that the probability of B given A is 1/3, and then they use this formula to figure out if they're equivalent. And so when they do that, they take the probability of A and B, which is 1/6, we figured that out right above, divide it by the probability of A happening, which was 1/2, and they multiply. What they do is they say, this is a division problem right here. So what we can do is rewrite this as 1/6 divided by 1/2, keep, change, flip, and that's what they do right here, and that's how they get that. They multiply and they get that it's 1/3, and yes, those two things are equivalent. And we'll stop there. We'll finish up 8, and then we'll start on the next section.